In this video, we're going to continue our generalization of some of the concepts that are related to the dot product. In this one, we're going to focus on a lot of the geometric stuff like length and distance and angle, as you can tell from the title. And to start, let's remind ourselves, going back to Rn and using a regular dot product. Remember we said that if you took the dot product of a vector with itself, what you'd end up getting is, in fact, in Rn it would look like this. It'd be u1 squared plus u2 squared, because again the components are the same, and then plus dot 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 un squared. So that expression is what actually shows up under the square root of the magnitude. So without the square root, we could say, well, this is its length or magnitude or norm squared, like that. Yeah. So that's the key. That's one of the keys to this whole thing, is just knowing this simple relationship between the dot product and the idea of length. Well, we now have a way of generalizing the dot product into now the inner product. So this then says, so before I write that down, let me just mention one thing. So if we wanted to find the distance between, let's say, two distinct vectors, u and v, again in Rn, it would be the magnitude of the difference between them, like this. So u minus v, take the magnitude of that, or the norm of that, and then obviously we can express this as a dot product. So this would be the dot product of u minus v, like that, with itself, u minus v. And now we would have to take the square root, because if I just do this dot product by itself, it's going to be the magnitude squared. So I got to take the square root of that, right? So with these two ideas, we can now talk about length and distance in any vector space, in fact, in any inner product space. And of course, then all the other formulas that we have involve one of these things, right? So if, for instance, the angle between two vectors, which might sound really strange to say, what is the angle between two polynomials? Or what is the angle between two matrices? Regardless of what that might mean in some other sense, we have a way of calculating it, right? So I don't want to get bogged down in this video as to about what it means, as opposed to how we calculate it, right? So yeah, so then let's kind of generalize it, and we just go down the list. So if we want to find the length or norm of any vector, in fact, let me go and say that so u and v are going to be elements in V, which is an inner product space, right? In other words, we have some defined way of combining these vectors, right? And now we want to define all these other things based on that way. So let me give myself a little bit more space here. Come on. All right, so so as far as the length or the norm of u, so this would be, so the norm of u, going back up here, the first one is just take the square root of both sides, and then you'd get the square root, but now it would be the square root of the inner product of the vector with itself, not the dot product, right? It's whatever we define as our inner product. So that's the way we would find the norm. What about distance? Well, distance is defined in terms of a norm. So then let's just say it this way. So if I wanted to find the distance between u and v in our inner product space, what I would do, in fact, I'm just going to go to, in fact, I'll write both. So you will take the norm of u minus v, and then, of course, that's now going to be expressed as a square root. So it's going to be the square root. But instead of the dot product, it's going to be the inner product. So it's the inner product of u minus v with itself. All right. Yeah, so that's distance. Now, I didn't write down the formula for angles, but let's say we wanted to find the angle between two vectors, so that we will use that cosine ratio. So cosine of theta is going to be, remember it used to be a dot product, now it's got to be an inner product, so it's going to be the inner product of u and v, and then it's going to be divided by some norm. So the norm of u, which again is an inner product, and the norm of v, right? So this gives us that theta is the angle, right, between u and v. And again, don't worry right now, is like, what does this really mean, right? Because it's hard if we try to impose our notion of geometry on these more generalized concepts, right? And then of course, so then immediately this gives us a way of defining the concept of orthogonality in the inner product space. And all we have to say is that, let me just write it like this. So u and v are orthogonal, right? If and only if their inner product is 0, however we define it, right? Here we go. And of course, you know, we could write down stuff about unit vectors and so forth. So the unit vector is where you take the vector and quote unquote divide it by its norm or its length and so forth. So I'm not going to state all of those. I want to get into a couple examples. It's one example, but it's going to require us to compute two distances. So here's the example that I'm going to do just to illustrate this concept. We could use any of the spaces that we want. But, you know, let's just use I'm going to go back to the polynomial space. So let's say that our v is p2, and let's say the inner product of any two polynomials in the space. This is how we're going to compute it. So it's going to be it's going to be an integral. So it's going to be an integral from 0 to 1. And all we do is we just multiply these things. So f times g, let's say dx, right? So here's the question that we have to ask. I'm going to write down 3 functions. One of them will be just x. Another one will be just x squared. And then the third will be x squared plus 1. So here's my question. In this space, is the middle function, so is g closer to f than it is closer to h? So is g closer to f or h? And of course, justify. So tell us why. Obviously, you know, because if we didn't, we would have a 50-50 chance of just guessing the answer, right? Well, when you talk about closeness, that's where length comes in, right? And what I'm going to do here, I will encourage you to, you can graph these pairs of functions. So graph g and f, graph g and h, and then maybe come up with some intuitive guess as to how you'd answer this based on the picture. But let's see if this inner product will give us a quantitative way of answering this, right? So what this means is we would have to find 2 distances and see which one is smaller, right? So let's find the distance. Let's do f and g. So let's do that one. So the distance from, or let's say the distance between f and g would be the length of their difference, right? So basically this magnitude right here, and which would be the square root of the inner product of f minus g with itself, right? So let's focus on what's going to go under the square root, because that's where the integral is going to come in, right? So f minus g, in terms of our functions here, it's going to be x minus x squared, okay? So then let's find the inner product of this with itself. So then the inner product of f minus g with f minus g. So based on our definition, it's going to be the integral from 0 to 1. And then we have to multiply this. So it's going to be the quantity x minus x squared squared. So we'll have to FOIL this out. Again, if you're good with perfect squares, you should see it pretty easily. And then if you want to write it in the standard form, it will be x to the fourth minus 2x cubed plus x squared dx, right? So we get a polynomial, which isn't too bad, and then we find the antiderivative, and we're going to use our FTC, so 1/5 x to the 5th power, and then minus 2 over 4, or that's 1/2 x to the 4th, and then plus 1/3 x cubed, and then we go from 0 to 1. So with the lower limit of 0, all we're left with is 1/5 minus 1/2, and then plus 1/3. So it looks like we can use a common denominator of 30. Yep, so 6 over 30 minus 15 over 30, and then plus 10 over 30. So that gives us an inner product of f minus g with itself at 1 over 30, right? And then the distance now is the square root of this. So we got to remember to take the square root. So the distance from f to g is the square root of this number. Okay, so not too bad. Let's do the same thing, but now find the distance from g to h, right? So let's do that. So the distance from g to h. So I need, yeah, so in fact, let me just write down this, let me just skip this step, because it's basically just restating what we did earlier with different letters, but g minus h, let's remind ourselves what those functions are. So g is x squared, and then h is x squared minus 1. So this would be x squared minus the quantity x squared plus 1. So look at what happens. That just gives us -1, right? So that's going to be a lot easier to find the inner product. So if we do the inner product of g minus h with itself, because the x goes away, it's just going to be the integral from 0 to 1 of -1 squared, because it's times itself, right? So dx, so that gives us 1x, and then we go from 1 to 0, so that's 1 minus 0, which is 1. And then, so the distance between g and h is the square root of this. You always got to remember to take the square root to get that distance, right, which is 1. So it should be pretty clear to you that 1 is greater than the square root of 1 over 30, right? In fact, let me write it like this. This is 1 over root 30. So definitely, so since, let's finish this up, since the distance from f to g is less than the distance from g to h, then our x squared is closer, yeah, so f, or put it this way, g is closer to f than h is, right? So that, you know, so the idea of comparing distances, that's not a new thing, but it's the idea of finding the distance. And when you talk about the distance between, let's say, polynomials, it might feel a little strange, but calculation-wise, you know, you got the integral and you got the comparison of the distances, so that should feel a little bit more natural. But you know, just allow yourself to kind of soak this in, and once you get used to it, the idea, once you have your inner product, then the distances and the lengths and so forth become a lot more natural, right? So hopefully, if this is your first taste of anything like this, it was yummy enough to encourage you to take another bite, and you can do that with me in the next video.